Giglio Power Infrastructure Engineering, advancing power infrastructure with expert FEM CFD Multiphysics engineering solutions. In this video, I show how I used COMSOL Multiphysics to model this 3-core cable by BHARA Cables using the cable selection and installation data shown here. The current capacity is focused according to the special climatic conditions in the Middle East. The steady state ampacity shown here at 505 amps indeed brings the conductor temperature just barely under the temperature limit. Here is the COMSOL Multiphysics FEM model. I use COMSOL Multiphysics because I like that it is designed for multiphysics and I just need to create the geometry one time, assign the materials one time, and create the mesh once for as many multiphysics coupling I would like to include in the model. Unlike other FEM software, you would need to create the geometry, assign the materials, and set up the coupling using some platform or something. And it involves many different project files. What comes to multiphysics is one project file, everything coupled together, and the coupling is actually automated. So for example, I have here heat transfer in solids, but if this simulation involves surface-to-surface radiation, or if it involves CFD, over here I just include multiphysics, non-thermal isoflow. This connects the laminar flow CFD physics interface with the heat transfer in solids interface, and here couples the heat transfer in solids and fluids interface with the surface-to-surface radiation interface. And I just need to set up the physics for each interface, and the coupling is automatic. So it's straightforward, easy to use. That's why I love COMSOL Multiphysics. In addition, in COMSOL Multiphysics, I can set up probes to monitor different parameters as the simulation is running. So I can create a variable for the conductor temperature, give it a variable name, right? And it's monitoring the temperature highlighted here, shown for the conductor boundary. And I can use this variable in variable expressions for electrical parameters. For example, electrical resistance, DC electrical resistance, AC electrical resistance, and compute the electrical parameters for the conductor losses, which include proximity and skin effects, compute the sheath losses, and overall losses. So it's using the temperature in the simulation as it's running as feedback, and updating the heat sources, which is used in the simulation. So in this simulation, I'm not using AC, DC, electromagnetics coupling. I'm not using electromagnetic fields for the coupling. I'm using actually IEC equations for the heat sources. But if I wanted to, or if required, I can easily use the AC, DC physics interface and set up the magnetic fields and electric currents physics for the coupling with the heat transfer interface. Very simple, straightforward. I'll show that in another video. Now let's look at the results. Here is the temperature distribution as a result of using the steady state ampacity 503 amps determined from the ampacity run, also showing the heat flux distribution. And here is the conductor temperature rise plot for the hottest conductor reaching steady state conditions. And now I'm going to demonstrate computing transient ampacity for 10 minutes. So what is the maximum current that the conductor can tolerate for 10 minutes without overheating, where I'm converting here the 10 minutes to years, because this model is set for years, right? And we're going to see now, all I did was change the time. So I'm doing this live. And I'm going to run the simulation, and we're going to see the conductor temperature rise. It'll take maybe, it says here, for the steady state, it took 14 minutes. So for the transient ampacity run for 10-minute duration, maybe about 2 minutes. So I'll speed up the video to skip this part, but transient ampacity is very important for applications where a large amount of current is needed for a short time duration. In this case, the ampacity applied is 1795 amps. For steady state ampacity, it was 505 amps according to the manufacturer, and according to the ampacity run, it's 503 amps. But for a 10-minute duration, the current increased to 1795 amps. Right? It's more than triple right there. So this, I'm computing it directly, no trial and error, no guessing. So this is saving time for anyone hires me for service. I get simulation results accurately, quickly, and I develop full detailed models. No approximations, no shortcuts, no cheating. I give you the full physics, full model. And for example, let me tell you, when would a transient ampacity calculation be necessary? When is it important? Well, some industrial manufacturing processes require a large current being drawn and applied for a short duration. It could be a few minutes, it could be an hour, or whatever the case. So industrial facilities, motor applications, right? Besides transient ampacity, I also I have a model for cyclic loading, where a motor is operating cyclically, or an industrial process is operating cyclically, or electromagnetic propulsion, where again a large amount of current is being fed by cables from a substation or some electrical room, right, feeding a system where the current drawn is a large amount for a short duration. Physics laboratories, where they have tacomac fusion reactors, where they're trying to harness the energy of the sun. Right, they're doing physics experiments in the laboratory that they use large amounts of currents, and this is not in the standard. So what I do, I specialize in custom power cable rating for complex installations that are not in the standard. So I have completed a lot of offshore wind projects and projects for utility companies in Europe, France, Spain. Now I'm focused on the Middle East, focused on the Mediterranean, and I am part Mediterranean, or mostly Mediterranean, background. Mediterranean Caribbean, actually. So here, the maximum conductive temperature is 89.851 amps in 10 minutes, converted to years. So this is direct, right? There's no other way. There's no textbook, no literature, no journal. You're gonna have to wait for my IEEE journal to come out soon. All right. Thank you for watching. Giglio Power Infrastructure Engineering is advancing power infrastructure. Contact us if you would like fully detailed multi-physics modeling to obtain accurate solutions without shortcuts or approximations. Visit our website at www.gpiengineering.com.